All right, let's go ahead and get started. Thanks everyone for attending week 4, our final week of the Python training course. This Saturday, the 28th of November, 2020. Today is going to be a lot of fun. We're going into machine learning and I'm excited about it as well. And it's a lot of material to cover. So for today, I'm going to try to see if we can limit our question to just the content that is being presented. That way we can actually go through the materials, and if there are other questions, we can save it for tomorrow, or we can continue to interact in the Slack channel. So there's a lot to cover. So let's stay focused on the class today, and I look forward to fun and exciting learning on machine learning. Um, so Vishal, with that, I would hand over to you. I will stop sharing so we can get it going because of the extent of material we have for today.
Sure. Thank you, Michael, and welcome everybody to another week of lecture. So let me share my screen, and hopefully you guys can see it. Can somebody give me a quick check on whether my sound is coming fine and the screen is coming okay for you guys? Yeah. Okay. All right. Sounds good. Okay. I need to. Okay. So in this lecture today, we will start utilizing some of the things that we have learned before, and we'll introduce another new package which is called scikit-learn, and this is essentially an introduction to utilizing Python for more hardcore data analytics and machine learning kind of workflows. So as I was telling you, so we're going to use the scikit-learn package, which is a package that actually helps to do machine learning in Python. There are other machine learning packages as well. These are the packages in scikit-learn are primarily, I mean, I have to be careful when I say this, but they are primarily focused on not deep learning, right? They are on the other, like they do not go into things like convolutional neural networks or some of the sophisticated machine learning techniques that we have, but they do cover a lot of the basic machine learning techniques like classifications, regressions using different methods, and you can see it in their website. This is their website, scikit-learn.org, and then slash stable. That's the uh, website. Right. Someone is watching a movie. Or maybe not. All right. Yeah, so essentially, this will start bringing a lot of the things that we have learned. So remember, just a quick recap of what we started off with. We started off from very basic, defining the data types and defining the loops and the functions and stuff like that. And then we started looking at a lot of different packages. So we have looked quite closely into the NumPy package and the Pandas package. And also we were doing a lot of plots on the last week's lecture with Matplotlib and Seaborn. So we'll start bringing a lot of those things together as well in this. So before I go into those details, I just wanted to quickly highlight what a machine learning workflow looks like in general. Again, this is not a standard way. I mean, it is a standard way, but there can be different variations of it. But essentially, on a higher level, in any machine learning workflow, which primarily depends on the data. A lot of focus and a lot of energy is put into the first two brackets where we gather the data and make sure it is in the right format and right data is collected, right amount of data is collected. There are no, if you're doing a supervised learning where you're training a network with answers that you already know, then you have to make sure that those answers that you're making the machine learn are good enough and has particular qualities and standards in there. So a lot of focus is on the data gathering and data processing. And once you have the data, a lot of your work is already done. Then you have to kind of pick up a machine learning model and train a machine learning model so that it understands and makes good analytical results from the data that you've gathered. Once you have that, then you go ahead and try to assess the results that you get out of these machine learning workflow and the trained models that you have. And this is an iterative process, so essentially a lot of time you will find that based on the type of model that you have chosen, maybe the data isn't adequate, maybe you'll have to add some extra features which are extra sort of information of the data. Maybe there you might find out that some of these data are not as per the data quality that you expected. You would also realize that there might be some other machine learning models that might be more useful for this particular problem. So you keep on doing this, and once you reach a stage where you are satisfied enough that the machine learning is giving you adequate and reasonable results for the problem that you have at hand, then you kind of freeze the network and then start predicting using the network. So that's overall the big picture of machine learning workflow. And we will try to utilize our the data set that we have been using throughout this course, the iris data set, and we'll try to do a classification problem in this case. So that's probably the first comment that I'd put in here. So um, we will use the iris data set for a classification problem. Now the classification problem here is defined as follows. So imagine, so if you remember from our previous lectures, we had this data set where we had different characteristics, let's say the sepal length, sepal width, petal length, petal width, and we had a species type, right? So we had three different species of flower, of this iris flower, and this was given to us. Now imagine if you were to frame this problem as such that you did not know the species type. So you just had the sepal length, sepal width, petal length, petal width. So that's the four features that you have from the data set, and you wanted to use those data to classify the different iris flower data set that you have into three different clusters or three different classes. The problem that we're going to solve, and we're going to see a lot of different ways of addressing this problem, and we'll try to cover different methods to do this, and we'll use the scikit-learn package to kind of address this problem, right? So all right, so that's the problem, and that's the data set that we're using. Some of these things that I'll do right now will be quite trivial for you guys. Now you have seen it over and over again. So we'll import the NumPy package first. We're going to use some of the NumPy operations. We will also use the matplotlib's pyplot plotting library to to do some plotting as well. So I'm going to import the matplotlib.pyplot as PLT. And you guys know this, that if you have to plot inline in the Colab notebook, then you have to add a line which says matplotlib, and the keyword is to have the plots inline, right? So now the next thing that we'll do is, so these are some of the packages that we'll use. Now we'll import the iris dataset. So I had shown you that we could use pandas, and we could import it from the CSV file that's on the web. But in this case, I'll actually import it from the scikit-learn package itself, right? So the scikit-learn package itself has some data set that you can use. It's not just the iris data set. There are some other data sets as well that you could use for learning and testing some of your hypotheses, right? So in order to import this, so the first thing that I'll do is I'll try to import the datasets folder from scikit-learn. So scikit-learn is called sklearn. So from sklearn, I'll import datasets. Okay, so that's how I import all the data sets that in there, and inside this data sets function, there is a load iris function, which actually helps you to load the iris data set. So what I'll say is my data set would be called, the variable would be called iris, and the way I load this is essentially I'll say data sets dot load underscore iris. So this is another just a way of, I wanted to demonstrate that you can use the sklearn's data sets to actually import the data iris data set. It's the same data set that you used before, so you could actually copy and paste things from your previous notebook and import the iris data set. It's exactly the same. All right, so now we have the iris data set. Now that we do in a data analytics and a machine learning kind of a workflow is to do some kind of data processing and actually visualizing the data and making sure the data meets the requirements. So one of the requirements, for example, for some of the algorithms is to have the data in a standardized format. So standardization or normalization is a way where you if you have a data that varies between a certain range, then you kind of use different techniques to bring them in between 0 and 1, or maybe some algorithms might require you to have them as a normal distribution. So um, those things need to be done before you do any sort of machine learning workflow. All right, so what we will do here is we'll do some data pre-processing, right? And in this we will visualize the data primarily. And this is again a recap from the Matplotlib class that we had last week. So we'll select the first two columns in the data set. So let's see what the data set looks like, right? So first of all, we should definitely look at that. So the data set is like this. So essentially it has four different, right? So these are sepal length, sepal width, petal length, petal width, right? So those are the four different columns in the data set. And what we will do here is that we will try to, and this would have other things as well. So this is essentially the way the data is arranged here is that if you do iris.data, that is the part of the data with the sepal length, sepal width, petal length, petal width. And then there is dot target, which actually gives you the species ID code, right? So 0, 1, 2. So these are the three different species. And you could also, there are other things in here where, for example, you could say dot target names, which would give you the names of the three different species, right? So it's all there in this iris data set. So what we will do is we will select the first two um, columns in the data set. So these are our features that we'll try to visualize and see if we can, if they are making sense to us or not. So let's say we select the first two features of the iris data set. So these, I am going to tell you that these are sepal length and sepal width. And we will visualize them eventually. So what I'll do is I'll assign these two columns into a variable called x, right? So these are my input features, right? So that's almost always, this comes from linear regression, right? Y equal to beta times x. That's how a linear regression is defined. Y equal to beta times x plus epsilon. That's the standard way. So that's a notation that we'll follow, right? So we'll say iris.data, and in here we will select all rows and we will select the first two columns. Okay, this is again something that you guys should be familiar about. And in Y, which is our target, we will say these are all the species ID, right? So iris.target, that's going to be our Y in here. Comment here, target is species ID. All right, I'll execute this cell. So I will have X and Y now. And now I'll try to plot the data, right? So again, this should be a revision from previous weeks. So we'll use plt.scatter, right, to get a scatter plot of things. So I'll plot the first column, which I know is the sepal length, and I'll plot it against sepal width, which is my second column. I will color it with my target species, right? So these are the three species IDs that we have, and I'll use a color map which kind of highlights this. So I'll say plt.cm.set1. That's a color map that comes inside the matplotlib library. That's a particular color map, and you could use your own if you want. And it's not a mandatory keyword to put in the scatter plot. You guys know this. So what I'll do is I'll put the X label as sepal length, and I'll put the Y label as sepal width. Okay, and that's it. I'll just execute this, and this is a plot. So a reason why we do this is because we usually using this visuals like this, it just makes it very easy to make sure that the data is reasonable. You get to see what the ranges of data is. You can also start identifying if some things are perfectly correlatable or not. So in machine learning, there's almost always a belief that you should not bias the data with redundant information, right? So if something is perfectly correlatable, like for example, if the sepal width and sepal length came up as y equal to x, like 100% correlated, then there's no point of using sepal length and sepal width in the classification problem, right? So that's one of the reasons why we do all these plotting. And remember, Seaborn has some very good plots, right? So Seaborn was a package that we discussed last time, and we had this pair plots in there that actually gives you a visual of all permutation combinations of the input features. All right, so far so good. Now the thing is, if you have multiple features, if your data, if your input features are higher dimensions, then it is almost impossible to visualize them humanly, because in human visualization, we have two and at max three dimensions, right? So in those cases, so if you had, let's say, 10-dimensional data, in our case we have 4-dimensional data, right? But if you had 10-dimensional data, then uh, it is often the people have looked at the problem, and people have tried to do some sort of dimensionality reduction, visualize the data better in a two-dimensional space or a three-dimensional space. And we're going to try to do that with our four features as well. So one of these dimensionality reduction technique, and it's a very powerful technique, it's called principal component analysis. So you guys should try and if you guys are not familiar about what principal component analysis does, you should look at at least its Wikipedia page to get an idea about what it does. But essentially what it does is it essentially does some dimensionality reduction. Okay, so based on the number of principal components that you are visualizing, it essentially it gives you a way of visualizing the data in the reduced dimension. And the way principal component works is that it tries to capture the components based on the variance in the data. So the first few components will capture the highest variance in the data, and then there's something called the scree plot that helps you visualize how much of the data actually captures how much of the variance in the data, right? So by capturing the variance, you are capturing most of the varying features in the data, and that way it's a good way of visualizing stuff. So anyway, so I'm not, without going into the details of principal component analysis, I just try to show you how we can do principal component analysis using sklearn package. So we'll import the PCA. PCA is basically principal component analysis. It's a standard acronym used for principal component analysis. We'll import the PCA module from the sklearn package. Okay, and we'll use it for our principal component analysis and the decomposition of the data. So what we'll do is we will uh, import the PCA package. So from sklearn dot decomposition. So there are lots of decomposition packages inside scikit-learn. And inside this decomposition, sklearn dot decomposition will import PCA. All right. So that's the module that we're going to use for our case. We will do the principal component analysis for all the data sets, so all the 4 features, but we will plot or we will extract only the first 3 principal components. And why we are doing this is because we can plot them in a 3D plot, right? So people would normally plot either in the first 2 components or the first 3 components, right? Because that's the maximum that we can, visualize. So we will do PCA on the iris dataset and extract the first 3 principal components, right? So how do we do this? So what I'll do is I'll call the reduced dimension as x underscore reduced, and we are doing this only on the input features. We do not do it for the output, right? Output is just one column. So we are reducing the input into the 3 principal component space. That's how I'll define this. So x reduced, that's the reduced feature space for the data, would be done using this PCA module that we just imported, PCA. And in here, it requires you to specify how many components you want, right? So how many components, how many principal components that we want. So that is defined by this keyword n underscore components. And we will say this is equal to 3, okay? So we want the 3 principal components. And then the way to do this is we will try to fit this transformation. So that's done using fit underscore transform. And inside this function, you'll have to specify what is your input that you want to do the decomposition on, right? So in this case, we'll do it on the entire data set. So that's iris.data. Okay. Hopefully that makes sense to you guys. I'll execute this cell. This gives me x reduced. And then what I'll do, I'll just use, we touched upon this last time. We'll use the 3D plotting tools to plot the 3 principal components. So plot the 3 principal components in a 3D plot. Okay. And to do that, we use this package. We say from MPL underscore toolkits dot mplot3d, we import axis 3D. So that's what helps us to plot our 3D figures. We'll say figure equal to, these are again, everything that I'm doing here should be a revision for you guys. We have touched upon things similar to this, very, very similar to this in our previous classes. So I'll specify the figure size, say 8,6, right? Then this is the main part where we do the axis 3D to get the 3 axis for the data, for the plotting. We will import the fig that we created. We say we have an elevation of -150, and we will visualize it as at an azimuth of 110. These are not something that you need to specify, but this is what you will help you, plot the data in a nicer way. You'll see that the results are, I mean, the plots look better with this elevation and azimuth. So after this, after we have specified the axis, we will use the scatter function inside this axis, and we will plot the 3 columns of the x underscore reduce, right? So what I'll do is I'll say my first scatter is x reduced all rows first column, right, comma. My second input is x reduced all rows second column, and the third one is x reduced all rows third column, right? Now, since in this case I already know the output species ID, so I'll try to color it using the output labels, right? The output species ID. So C equal to Y. And I'll again use the same color map that I used in the previous plot. It's called plt.cm.z1. Now for the size of the scatter points, I will use a size of 40. Okay. And then you can do the usual stuff of labeling the data, the axis and whatnot. You can put a title, you can put a label. So I'll do the title and the labels. So I'll say ax dot set underscore title is so I'll say it's first three PCA directions. Okay. So these are the first three. So it's based on principal component analysis is based on eigenvalue decomposition, and these are the three different directions, right? So my first label, which is my X label, it's essentially first eigenvector, or some people say first principal component. The Y label in my case is the second eigenvector, and the Z level is the third eigenvector. Okay, that should be good enough. Let's execute this and see what we get. So right, so now you're trying to, so these are not sepal length, sepal width, or petal length. It's some combination of that you've decomposed using the principal component decomposition. But now it helps you to visualize the data, and you can use the scree plot to find out. And I did, and you can see that this first three component actually captures almost more than 90% of the variance in the data. So far, so good. So,
Vishal,
yep.
quick one. Did you display, before we started, did you display a table of what the full data set is, like so that we could see? Do you
Yeah.
put a line of code to display just the full data set? Yeah.
So I could do that. So it's essentially iris.data has the four components. So it's a array with sepal length, sepal width, petal length, petal width, right? So that's our data, and iris.target has the species IDs in it.
Okay.
No, good point. So I'm going to put a um, target data and input features. All right.
Hey Vishal, how do we know that the first three components cover the 90% of the variance in the data?
So in principal component analysis, I think it's called a scree plot. So if you do a scree plot of your principal component like that's in there, so a scree plot essentially tells you, if I get a figure of this, so it tells you that given the number of components that you're looking at, what is the corresponding, so instead of the eigenvalue you can plot it against variance. So it'll tell you, like, for the first, and it'll look just the opposite of what it looks like here. And based on this, you would see that it plateaus at some point, right? So after, let's say in this case, the variance plot would look just opposite to this. But we can say that after the most of the variance is captured in the first two components, then we have a little bit in the third component, and below this is almost like not very significant in terms of the variance capture. So that's how you kind of decide how many components you should look at.
Perfect. Thank you.
Yep. And in scikit-learn, you can easily plot a scree plot. You, you can try to see that and let me know if you have problems. And there is another question: what are the other useful techniques in useful decomposition techniques in scikit-learn? Scikit-learn has a lot of decomposition techniques. You can look at them, but MDS or multidimensional scaling is one of the most useful and sophisticated way of visualizing high dimensional data, and scikit-learn has a version of it inside the package. All right, so now what we will do is we will try to go into more of things that we do in machine learning. So in machine learning, what we have this terminology where we define the data set or split the data set into different components. So we say we have a chunk of the data that we use for training the models, right? So you will see that a lot of machine learning depends on hit and trial or trial and errors, right? So you use a part of the data to do all of those things to make the model architecture, design the model architecture and whatnot. And then there is a separate set which is called the test set. And in the test set, you can also have two separate components. One is the validation set. So what happens is, you keep a chunk of the data and you try to do your more finer tuning or the hyperparameter tuning using the validation data. And then you have a third set of data set which is called the test data set, which is completely blind to all of your training process in the machine learning workflow. It's completely blind, and that is the ultimate test that you would have, right? So you would train your model, you will make sure it does what it's supposed to do. You validate it using the validation data set, and then there is this blind data set where you apply this machine learning model and then see if the machine learning model actually performs well. And this is the exact same format that's being used in some of the major competitions that happens, right? Like, you guys might know about Kaggle and others. So they do the same. They keep a part of the data set separate so that you do what you need to do using the data set that they give you, but the final test is on that separate test data set. So using scikit-learn, we can actually split the data set into training, validation, and test set. Or in this case, I'll just split it into two
Hey, Vishal.
pieces.
Sorry,
Hey,
there's a quick question.
yep.
David is asking, he needs to see the original PLT statement. And if you can put that in the chat.
Uh, can I see the original PLT statement? Sure. This one? Oh, is it? Oh, well, the original PLT statement. So is it import matplotlib dot this guy?
Hey, David, can you come off mute and confirm? Oh, mic is not working. Line 12.
Line 12. Well, there are
Just
no line
scroll.
numbers in here, but are you mentioning cell 12? Um. Anyway, so
Okay, just
but
move
I
on.
guess,
I'll provide the
yeah.
information. Yeah.
Okay. All right. Thanks, Michael. So I think this is probably the PLT line here, and this is another PLT use where we did the scatter plotting, right? And this is the final one where we are doing the three principal components plot. And I'm going to I think Natalie has actually pasted that in the chat box, so it should be good for you guys.
Thanks.
Yep. All right, so where was I? So I was telling about the splitting of the data set, right? So let's try to use sklearn's package to do this splitting. So split dataset into training and test sets. Okay. So now what I'll do is, although I did have the X and Y, so I'll start off fresh in here, and I'm also taking this opportunity to showcase you guys, the different ways of accessing the data set as well. So what I'll do is I'll say iris underscore X and iris underscore Y. So X are on my input feature, Y is the target, is equal to the data sets that we had imported from sklearn and load underscore iris, right? So that's the data set. And in here, I'll put the return underscore xy is equal to true. So this will actually give you the data set. Okay, so that's another way of accessing the input features and the output targets. Now, one of the key aspects of defining a training and the validation or the test set is to split the data set randomly. Okay. So, and why you need to do this is because you want to have an unbiased way of splitting the data set. You shouldn't be biasing your splits of training and validation on the test sets based on your prior information. That might be actually very, very harmful for your machine learning models, right? Um, so yeah. Um, so anyway, so randomly is a key word here. So I did add that in the comments, split data set randomly. And the way we do that, and you've seen this possibly before. So we'll use the NumPy random package to set the seed of the random number. So what does this do? So setting the seed of random number helps replicate results, right? So if you didn't set the seed, every time you do this, you would get different results because based on the random number that got picked up, your training and the validation set becomes different. But we don't want them. We want them to be selected randomly, but we want to replicate and reproduce the results. It's mostly reproducibility, right, of the results. It's a big thing in the machine learning community. All right, so what I'll do is I will say that indices is equal to np.random.permutation, and then we will say length is equal to iris underscore X. What it does is basically it will give you the indices, but it'll randomly do some permutations on them, right? So instead of having 0, 1, 2, 3, 4, it will say 0, 10, 100, 20, 500, whatnot, right? But it'll give you the exact number as the length of the iris data set, right? So it's taking the row indices and it's doing some permutations on this. And this actually, shuffles the data, right? So now what I'll do is I'll just say, okay, well, now my data is shuffled. Now I'll just select all the data, leaving out last 10 samples for testing. So that's my testing data set. So it's not picking up, if you had 500 rows, it's not picking up from 491 to 500. It's picking it from this random indices. That's the key, right? We need to do this before we select the data. So I'll say select all data randomly, leaving out 10 sample points for testing, right? So in this case, I'm using the native NumPy package to do this. And if we have time, I'll also show you that, in sklearn, there is a module which can help you do this without going through these 3 lines of code, okay? But this is using the NumPy package. So what I'll say is iris underscore x underscore train is equal to all the data from iris, and I'll pick all the indices that I have right in here, and then I will pick everything except the last 10, right? And this is again a notation that you guys should be familiar with, right? So this is my X train, and I want the corresponding Y train as well, right? Iris underscore Y train. And this is from the iris Y data. And again, picking up all the rows except the last 10 from this random indices. Now, rest of it is my test data. So iris underscore x underscore test is the iris x. And in this case, I'll pick the last 10, right? Minus 10 till the end. That's how we define this. And similarly, I'll have to do it for the y test. Okay. Iris underscore y indices minus 10 to the end. So this gives me the training and the test data set. So X train is the input features, Y train is the corresponding outputs, X test is the input features for the test data set, and Y test is the corresponding output.
Abhishek, is there a rule of thumb in terms of the number of how do you split the data set into train and test? Is it 80, 20, 10? Is there any rule or you just
There isn't any hard and fast rule. It depends on the amount of data set that you have, right? So
yeah,
if you have the luxury of having a lot of data set, then there is often this 80-20 rule, like
yeah,
80, 10, and 10, right? So but if you have a very small piece of data set, then there are things like cross validation, k-folds cross validation, where you systematically, so you have such a small data set that if you leave out like 20% of it, you might not have sufficient
yeah,
data set to train the model. Then what you do is you would split the data set like k fold times, like k number of times, but leaving a chunk of it each time. So that ways you statistically it can be proved that you have kind of done some rigorous cross validation in there. So that's another way of doing it. But I don't think there is a specific rule of thumb.
okay, thank you.
Yeah. So far so good. So we had almost done our first part, so which is visualizing the data and processing the data such that we can input them into our machine learning model. Now is the next part, which is the exciting part. Hopefully you guys are all waiting for this. So we'll train, or we will introduce our first machine learning model. So our first ML model for the classification problem, right? And the one that we'll use is what we call the k nearest neighbors. So essentially what it does is it's a classification algorithm, and it looks at clusters of the data, right? And then it will try to analyze the training data, and those have their species ID mentioned, or specified in them, and they will try to make some boundaries in the data, right? So based on those boundaries, those are the cluster definitions, right? So once you have a new data set, and based on the proximity to those boundaries, it will then classify it whether it's class 1, class 2, or class 3. Okay, so that's in one line k nearest neighbor description. All right, so here we will again use sklearn package for this. So we'll say from sklearn dot neighbors, we'll import k neighbors classifier. Okay, so there's a classifier, there's a regressor as well, and I guess you guys might be familiar with this. Classification problems are ones where you have discrete values, like you have class 0, class 1, class 2. Regression problems are where you have continuous values, right? So you'd have the output would not be classes, but it'll be a continuous variable, which can be, I don't know, let's say a housing price or whatnot. All right, so we imported the k neighbors classifier. Now, this is where, this is how almost all of sklearn's models work. And this is how it is done for not just k-nearest neighbors, but for other machine learning models as well. And we will see this in the some of the other examples. But we first define the classifier and then we fit the classifier. Okay, so we define the classifier with, you can specify different hyperparameters for the classifier. And once you have defined it, you fit it using the training data set. Okay, and then once you have fit it, then you do the prediction based on the test data set. So that's how most of the machine learning models would work in sklearn. So like I said, the first step is to define the classifier. Okay, so the way we do it, we say knn. Okay, k nearest neighbors is k neighbors classifier, which is essentially this guy here. So I'm going to copy this, and we will just go with the default parameters for this. Okay, so we're not going to change all of the hyperparameters. We can do that later, but right now we start off from the default parameters. So once we have defined the classifier, we'll train the classifier or ML model with the training data set. Okay, so the way to do this is you call the classifier, which is a function, right? So knn dot fit. Okay, so that's how you do it. And then you specify your input, which is your x train, iris underscore x underscore train, and the corresponding outputs. So this is a supervised learning method, right? So you need to have the corresponding labels, which is another terminology that you'd hear a lot. So that's how, you give the features and the label. Okay, and that's it. You just execute this. It gives you the information about the neighbors classifier, the different parameters that it's using, and remember, we are using all the default parameters for our first case. All right, so that's it. So it had taken the data, it had trained the data on this training data set, and now we'll just use this trained machine learning model to make prediction on the test data set, let's say. Okay, and you could have used it to predict on the training data set as well, but the real test is on prediction on the test data set, right? Because that's not what was used in the clustering. Prediction using the trained network on the test data set. Okay, so what the way to do this is you call the classifier again. So instead of doing dot fit, you do dot predict. Okay, pretty intuitive in there. And in this case, it just takes in the the input features and not the output class labels, right? So in this case, our input features would be x underscore, oh sorry, iris underscore x underscore test, right? So this will give us, these are all the class IDs, right? So a way to visualize this is, I'll put this inside a print statement, right? So this will print it out, and I'll also print out what was my true label. So remember, in our test data set also, we had the actual labels, and we know what the answer should be, and we can see what our predictor did in here. So we'll say iris underscore y underscore test. That's our true labels, right? So not too bad, right? So it has classified, majority of the stuffs, as the true class labels, right? So the only one it has missed is this guy, right? So it misclassified the second sample as a class 2, but the true value was class 1, right? All right. So now, yeah. So let's see. The now I have a question that can we see the confusion matrix? As we can, but just to give you guys an idea about how we can visualize this. KNN is one of the classifiers that can be visualized very nicely because it's dependent on the clustering, right? So I'll copy and paste a code which you guys will I'll also copy and paste it in the chat window. It's a little bit involved, that's why I'm not going through this in the class, but you'll get it in the notebooks that we send you, and also in the I'm going to copy and paste this in the chat window so that you guys can also try and execute this. And you will see that almost all of the things that's in here, it's some things that you have seen before. It's not something that's new. But what I wanted to show you guys is that, out of this, you can actually find out, how the classification is made. So it's a plot of your input features, right? The first two features is what it's plotting, and then it is classifying based on how a point lies based on these different class boundaries, right? So it's a three class classification. So, and these are two different ways of doing it. One uses the weights to as a uniform. One is based on the distance, right, of a particular data point. So yep. So that's something that you guys can look at it later at your own time. But in the interest of time for this class, I'm going to not try to uh, you know um, go into details of this. But but I definitely think the question that Midova had about confusion matrix is pretty important. So let's um, try to address that here. Okay, so now we have gone past the stage where we have trained the model, and now we are trying to analyze the results. We've also used it to predict, and now we are trying to analyze the results. And we might have to repeat a lot of our steps using the same kind of workflow with different machine learning models and whatnot, right? So this is a step where we say we analyze the results, okay? And one of the way to analyze results is to view what is called the confusion matrix. So the confusion matrix can be very confusing, but it's actually meant to not be confusing and be actually pretty self-explanatory. Let's try to explain that when we have the confusion matrix. So essentially, the confusion matrix tells you about things like um, if you have how many misclassifications you have, how many false positives you have, how many false negatives you have. There are different other metrics that's defined as well, like the F1 score. You would hear about that, and the F1 score comes from concepts like precision and recall. So these are some things which are there in the lingo. People use it for different kind of purposes, and I strongly recommend you guys to look into some of these definitions because they can be pretty handy. But let's try to just get a simple confusion matrix first and see what it has for us. All right, so thankfully in scikit-learn we have a confusion matrix that we can use a function, and also we can plot the confusion matrix, so the plots look even prettier. So if you're doing any presentations, or if you're writing a article or whatnot, you can plot the confusion matrix as well. So from sklearn dot metrics, so dot metrics has all the different metrics that you can think about that's in the package. So we will import confusion matrix, okay? And also, because we'll try to plot this as well later, we'll say from sklearn dot metrics import plot underscore confusion matrix. Okay, so one will give you the confusion matrix and another one will help you plot it. And it's a very, very complicated step. So I'm going to go over this very slowly. But what you do is you say confusion underscore matrix, right? And then remember in the previous section we talked about this. So it's a knn.predict helps you predict the uh, predict the class labels, right? So knn.predict, that's the way we predict. So these are the predictions from the test data set, let's say x underscore test. And we, in order to have the confusion matrix, we'll also have to, give the true labels as well, right? So the same way that we were printing it out, so that way, so the first part is the predicted labels and the second part is the true labels, right? I guess that should be it. So it was pretty darn difficult, a one line of code, but um, yeah, it gave us what we needed. So sklearn actually helps us to do all of these things pretty easily, is what I was trying to say. So essentially, what this confusion matrix tells you is that you have the different. This is as a matrix, so you have three classes. So it's a 3 by 3 matrix. So the first one is class 0, second one is class 1, third one is class 2, and on the diagonals, what you see is how many of the predictions were actually successful. So in class 0, you have 4 labels, and out of them, all 4 of them were predicted correctly. But if you look at class 2, and we saw that we had 10 samples, so we actually printed it out. There were 2 that were predicted as class 2, but there was 1 that was predicted as class 1, right? So that's how the confusion matrix works. And a better way to describe this is to plot it, right? So we'll use the plot underscore confusion matrix function. And in this, what it takes is, it takes the estimator, which is our KNN, right? That was our classifier. Uh, and we will do this again on the test data set. So it'll take the X, right? So X is our iris underscore X underscore test, right? And Y are the true labels, right? So we do have the true label. So iris underscore Y underscore test, right? And in this case, I'll use a color map that you will see in almost all the publications that come out of plotting confusion matrices. I don't know why they use it, but it looks pretty cool. And there you go. So essentially, the colors, they tell you even better story. So if you had everything along the diagonals, if the colors would be completely dark on the diagonals, then it would mean that you have done pretty good. But as you see, colors on the off diagonal elements, that would mean that there are some misclassifications that happen. That's how I understand it. All right. So we have our first machine learning model that did pretty well. And we did actually cover all the steps in there. Okay. I think this might be a good point to take a quick break or ask, questions till this part, things that you couldn't follow or stuffs like that. So I'll halt here for a bit and open it up for any questions, specific questions that you had on what we described today. And if not, we might take a quick break. What do you think, Michael?
Yeah, maybe it's a good time for a 5 minutes break. Then let people ponder. Then when we come back after the 5 minutes break, we can take questions before we continue.
Yeah, I'm guessing we should all get confused with the confusion
Yeah,
matrix.
as the name implies. so, so let's take a 5 minutes break. We'll be back at 3:08, and then we can take 1 or 2 questions.
Perfect. Sounds good. All right, it's 3:08. A quick check on any questions or anything in the lecture so far that was um, confusing, or do you guys want me to go over again? I take the silence as you guys have understood or are following what I'm trying to explain here. So I'm going to go forward and try and introduce some more machine learning models, right? So we saw our first machine learning model, and let me actually go back to where we started off. So we gathered our data, right? So we had our iris data. We did some pre-processing. We visualized the data. We did a principal component analysis to look at the different principal components. Then we split the data into training and the test set, right, using the NumPy's native random function. And then we use the k-nearest neighbors classifier to train a machine learning model with the trained data. And then we predicted using the trained machine learning model on the test data. And then we did what we call the confusion matrix to predict or to analyze the data and see how good our model did, right? So now let's say you showed these results to your management, and they said that, oh, let's try some other machine learning models and try to compare how those results look as compared to the k nearest neighbors, right? So that actually brings us to the next part, right? So where we will try to use another classifier to classify the same training data and see what the classification results look like. Okay, so I'll insert a new line of code, and what I'll say is using another machine learning model. And this is another famous one. It's called logistics regression. It's essentially similar to linear regression, except for the fact that it's used for classification purposes and uses in its native formulation, it uses the logistic function, which sometimes we would hear as a sigmoid function, right? So it looks like um, I don't know, S-shaped, and it tries to estimate the log odds of a particular class. So it gives you the probability, and based on the threshold that you set, you would say that, okay, if it is below this set threshold or above this threshold, we will assign it to one class versus another. Okay, so that's 1 minute description of logistic regression. So again, we'll follow the same scheme from scikit-learn. So we'll say from sklearn, we will import linear model. Okay, we will define the classifier, right? So previously we had the KNN. So here we'll have the logistic regression. So we'll call it log underscore reg, logistic regression. And we will invoke the linear model that we imported. And then inside it, there is something called logistic regression. Okay. And we'll use the logistic regression has different parameters. So I'm just going to use one keyword, which is C equal to 1E5. And you can take a look at the help of the linear model logistic regression, what exactly this does. Okay, so once we have defined this, we will fit the classifier, right? This was our same scheme of doing things before. So what we'll do is we'll say log underscore reg, which is the logistic regression dot fit, and we will input the iris x underscore train, and we'll say iris y underscore train, right? So that's how we would define it. Right, so it gives you again the regressor, which was defined in here, and it fit the regression using the training data set. And now we will again do the same thing. Now I'm going to skip the confusion matrix like output and just plot the confusion matrix, because that's more visually appealing and gives us the information that we want. So what we'll do is we'll use what we had imported before, plot underscore confusion matrix. So the way it is defined, remember, so we first have the estimator, then we input the input features, iris underscore x underscore test, and then we give it the true labels for this data, right? So iris underscore y underscore test. And again, I'll use the color map as plt underscore cm dot blues. Right. See what it does. So again, we see that somehow this, but so oh well, this is actually different than, oh no, it is the same. So in this case, we are seeing that one of the class 2 labels were predicted as the class 1 thing. Yep. So there's no improvement in this case, but we did check another machine learning model. All right. So now we will do something even more fancy. So we will do what is called the random forest. So you might have heard about decision trees or cart is another way of doing this, or random forests. So these are different variants of using decision trees to make classifications. So we're going to try to utilize that particular method for our classification. So let's say third ML model, and this is random forest, right? So again, what we'll do is from sklearn dot ensemble. So these are all ensemble based uh, models. So sklearn dot ensemble, we import random forest classifier. Okay, so that's our random forest classifier. Then we again define our classifier, define the classifier. So we'll say in this case R forest, random forest is equal to random forest classifier, and in here I will say as the parameters, and you can see what each of these parameters mean. So I'll say the number of estimators is equal to 100. That's actually the default value. The maximum depth is none, right? So that's another default value. And the minimum sample size, sample split. So the way the trees work is you have to split the tree based on different decision, decision parameters. So it's a very interesting concept. You guys should definitely look at it. So all those things, we're keeping it as default, and we'll say that the random state is equal to 0. So random state actually tells you that you can reproduce the data set or the results once you have executed it. So what I'll do is I'll just put comma random state is equal to 0. Okay, so that's the only thing that I do, that I specify. You could have by default it's equal to none. So you could have also tried your first run with just all the default values. So, but anyhow, once we have the classifier defined, would fit the classifier using the training data set, right? So let's say R forest dot fit, right? The same philosophy that we had before, the same type of formatting. We'll say X train, iris underscore X train is our input features, and iris underscore Y train are our output labels, right? So that's it. So it has done some cool stuffs in here, um, and it also does bootstrapping, which is another very cool concept in statistics that you guys should possibly look into if you want to do data analytics. Uh, yeah, and by the way, Brad Efron, who is the inventor of Bootstrap, yeah, he's was one of my favorite professors in Stanford. He's pretty cool, and yeah, a lot of these classifiers, random forest classifiers, actually came from the statistics department back in Stanford. and yeah, it's a very cool uh, way of doing stuff and very, very popular. Anyways, uh, so yeah, so now that we have fit the classifier using the training data set, now we will again plot the confusion matrix, right? Um, we would put the estimator in here, and then we will say iris underscore x underscore test is our, you know, input feature. Iris underscore y underscore test are our true labels. And again, I'll use the column map as plt.cmap.cm.blues, right? So again, for some reason, this class 2 is always getting misclassified, right? And you can test this using the training data set as well, right? So we are just looking at the test data set, but you could also do this with training data set, right? And see, like, in the training, did it do a perfect job of fitting the data? So it did, right? So you can see that all the values are in the diagonals, the off diagonal elements are all 0. This is perfect. So but this actually introduces the concept of a variance and bias, right? So you might overfit the training data set, and that is why it is so important to have a test data set that you are using for validating the results that you have, right? So if you had included all your results, all your data into the training of the model, then you might get perfect results for that data set, but that actually is prone to overfitting the training data set, right? So yeah, that's another side comment in there. Okay, so wow, let the fire brigades go away. Not sure what's happening there. Okay, so now we have three different models. So we had the k nearest neighbors, the logistic regression, and then the random forest classifier, right? So you have these results. You went to your management, and they said, like, you know what, the buzzboard around the corner, or in our field, is on neural network, right? So let's try. Why don't you guys give a try on the neural network architecture? So it'll be like, okay, fine, so let's neural network, and we have sklearn to our rescue, right? So we can use a simple feed forward backpropagation neural network, which were the earlier versions of the neural networks, right? With neurons, you might have seen them in different pictures, right? So these are not deep neural networks, but the simple neural network. So we can try that using the sklearn itself. So we will, let's say that, our fourth machine learning model is a neural network. Okay, again, we'll follow the same things that we have done before from sklearn. Now these are neural network package. So we'll say dot neural network, we'll import MLP classifier. So that's a basic neural network that we use for the feed forward backpropagation kind of a workflow. So again, now we define the classifier, right? So that's the NN, which is neural network. I'll say MLP classifier. And let's actually first see what the default values are. And we might have to change a few if required. Okay. So we want the solver to be LBFTS. So that's the standard one that we want to use. So we'll specify that. Possibly that's not in the uh, in the uh, in the default settings. So it's actually Adam that's used. But Adam is also a very good solver, by the way. It's actually used much more in the deep learning optimization problems. Yeah, I wish I could go into details of this, but Adam is adaptive momentum basically, and the reason why you do all of these things is because you do not have a guarantee that your optimization loss function is convex in shape. So you might have not just a global minima, but there might be local minima where the algorithm might be stuck. So that's why you have to use something sophisticated. But anyway, so that's a side note. So we'll use the solver in as the LBFGS. That's the solver that we will use. There are a few more parameters that I'll change in here. So the alpha, which is the learning rate, essentially, I'll make it a little bit higher than the default one. So the default is 0.0001. I think for this problem, I can actually start off with a pretty higher learning rate. So the learning rate essentially defines how much of your weights that are being optimized in a neural network architecture, how much they can vary in between the different iterations, right? So that's what it's done. Now, the other thing that I have to do is I'll have to define the architecture itself. So that's done using the hidden underscore layer underscore sizes. So I'll use architecture that has 5 neurons in the first layer and 2 neurons in the second. Okay, and the last one, use the random state equal to 0 because I want to get the same results each time I run this. Okay, so this is how we define the neural network. That's a one-liner, as you saw. And then you can, do the fitting. So I'll use the x underscore train as my input feature, iris underscore y underscore train as my labels, right? So that's about it. So you run this, it doesn't take a lot of time, right? It's done a maximum iteration of 200. Um, and yeah, so it has also, tried to look at the different parameters that you mentioned. So I'm curious, I might be wrong when I say alpha is the learning rate parameter. We might have to check that because there is also another keyword that I see here which says learning rate initialize. So that might also be the learning rate. So I'm not sure what alpha in here is, but alpha is also uh, most commonly we use it as a learning rate as well. So you might actually go into this particular classifier and see what it actually means in this case. All right, so in the meantime I have also lost the connection to this machine, but let's see if it can reconnect. Maybe it's worth moving to a new one. Not so. What we'll do is we'll do the same thing, right? We'll plot the confusion matrix using this neural network based architecture. So we'll say NN, our estimator, iris underscore x underscore test, iris underscore y underscore test, and color map is equal to um, plt.cm.blues, right? Perfect. So in this case, it actually did even worse than the previous one, right? So now it has classified one of these class 2s as class 1 as well. So it actually didn't do as good as what we wanted it to do. And you can, as you know, so remember we have the nn.predict, right? So we can actually look at what went wrong, which ones went wrong. So we can actually do nn.predict, and then we put just this, right? So this one actually is asking us to reshape the whole thing. So that's why it's better to try to use this kind of a specific format. So I think we have a different format for the neural network architecture. So iris underscore x underscore test, this should be pretty standard. So let's see. Oh, sorry. So instead of using the y, I should have the x, right? So that's what was giving us the error. So, and this one is what we are predicting. Print that. And we can also print, because we have just 10 samples, we can actually look at each and every sample, right? So we can do print y iris underscore y underscore test. So you can see that, this one is misclassified. That was a class 1, which has been classified as class 2. And then there is this one as well, which got misclassified, which was class 1, but it was classified as class 0, right? So that's the two, you know, misclassification in the confusion matrix. All right. So now I did mention that, you know, um, we can use some of the other pre-processing techniques using sklearn's pre-processing modules, right? So one of the machine learning algorithms, which is called support vector machines, and there are different school of thoughts, have different you know, philosophies around this, but the way it's recommended is that you should normalize the data such that it has a 0 mean and 1 standard deviation before using support vector machines. So, and this might be something that is also useful for other cases as well, and also in deep learning architectures, that you might have to standardize or normalize the data to make sure that, you know, you get better convergence. So let's see how we can normalize the data using scikit-learn. So normalize the data. So to do that, what we'll do is we'll import from scikit-learn, we'll import the module called pre-processing. Okay. And what we will say is that we will transform the iris underscore x into iris underscore x underscore norm, which is the normalized version of this, right? So, and we'll use this pre-processing package. And inside this, there is a module called normalize, right? And you can specify what sort of parameters you want, but the only required thing for this is the input features, right, that you want to normalize. So this actually would give you iris underscore x underscore normalized, which is the normalized features for iris underscore x. And you can actually visualize that. So let's actually try to see what iris underscore x underscore norm has inside it. So you can see that all these values are you know, decimal. It's mostly centered around 0, right? 0 mean and standard deviation of 1. So that's what it gives you. And this was essentially the initial um, values that you had, right? So you had values like 5.1 and whatnot. So it has done a normalization column by column. So that's also important. So it didn't do a mass normalization, it did it column by column, but you can specify how you want to do it. But that's uh, that's essentially the way it does the normalization. So there's a question, is the default log normalization? So let's check that. So I don't think so. It's doing a log normalization here. The log normalization would be done for specific cases where you have a log normal distribution. I don't think here it does that. It actually does a, um, a pretty standard normalization. So it's basically doing the 0 mean and standard 1 standard deviation. It's what I'm guessing. But I definitely encourage you guys to actually look at, you know, the help in more details, and I'm sure they will have, you know, what they're doing the normalization with, right? Okay, so now that we have this and use this again, so remember in our previous like, you know, previous cell, and I'm going to go up here to just make sure that you guys remember this. So we had, you know, this iris x. Now we have iris underscore x underscore normalize, and we are going to use the same philosophy and the same you know, technique to get the new training and test data set. The only difference being that, you know, instead of using iris underscore x, we will use iris underscore x underscore normalized, right? So because that would be our input features. So what I'm going to do is I'm going to copy this part of the code, right? This was there before where you had the indices and you had selected your training and the test data set. I'm going to copy this and I will come down to the cell I was before. And the only difference that I'll have to do is, instead of doing train, I'll do train underscore norm, and I'll do x underscore norm, right? So this ways I have the same exact same indices as well. So I could have done the randomization again, but that's actually not required in this case. Sorry. So yeah, that should give me the two different features with the normalization done on them. So okay, so now I have these two. So what I'll do now is I'll use support vector machine, which is another way of classifying. So it was very famous before the deep learning era for sure. Like it had a lot of traction, but now it has lost a little bit of its popularity because it's hard to train a little bit. But yeah, nevertheless, we can actually try our data set with the support vector machine. So support vector machine, and I'm going to use, so there are different variants of support vector machines. So I'm going to use the one with the radial basis kernel, which actually fits a radial basis function to define these supports in the support vector machine algorithm. So support vector machine SVM. I'm going to write this down as complete support vector machine with radial basis function as its kernel, right? So again, as before, we'll import the SVM module. So it's a separate module in sklearn. From sklearn, we import SVM. So yeah, so SVM was very powerful until few years, and they have a separate module in sklearn. So what I'll do is I'll define the classifier, right? So I'll say SVC underscore norm, right? So that's my classifier support vector SVM underscore norm, right? So that's our classifier, and to do that, what I'll do is I'll invoke the SVM that we imported, and inside this we have the support vector classification SVC. Okay, and because I'm using the kernel as the radial basis, so I have to define that. That's not the default, so I'll say RBF. That's a radial basis function for the support vector machine. Okay, so that actually defines the classifier. So now, as we do before, we will use it to fit our data as vm underscore norm dot fit, right? We will use our normalized data right now. So we'll use iris underscore x underscore train underscore normalized, and the output labels would be iris underscore y underscore train, right? So that didn't get normalized or whatnot. All right. That actually gives us the classifier, right? So it doesn't take a lot of time given the data set that we have and the powerful machine that we have got in here. So now we'll use this to actually visualize the confusion matrix on the test data set. So let's say plot underscore confusion matrix. And remember, this is using, first would be the estimator, right? SVM underscore norm. Now our test data set in this case has to be also normalized, right? So that's the prerequisite. So your input and so your the training data distribution and the test data distribution should be the same. So that's why you'd have to use iris underscore x underscore test underscore norm, right? So that's your input features, and iris underscore y underscore test are the true labels, and we'll use the column map as elt.cm.loose. Let's see how it does. Okay, so again we are back to the place where we have one misclassification in class label 1, right? So that's the one that's having some misclassification in here. I wonder why this one is so difficult. Maybe yeah, I'm not sure if the separation between class 1 and class 2 are so hard, and one way to analyze this is to just do some more plotting and see what's going on with this class labels, especially for this particular data set that we are considering as a test data. Okay, so we have now got a bunch of machine learning models, and we have seen, how we plot the confusion matrix. Now, another thing that is often used for classification problems are, precision and recall and F1 score, right? So using sklearn, you can do that very, very easily. So you can, this is often called classification report, right? So, and it helps you to identify, how good your classifiers are. And you should definitely look at what the definition, precision, recall, and F1 score are. But these are related to essentially the false positives and false negatives, or they also call them type 1 error, type 2 errors, and stuff like that. Anyhow, so we'll see how we can get this classification report. So we'll say from sklearn.metrics. So remember, this was again the same thing from which we got the confusion matrix. We will import the classification report in this case, right? So, and we'll print it out, right? So we'll print classification report. Okay, and inside this, the things that it takes, and you can, if you execute this cell, you will get to know what the inputs are. Right, so you need the true labels, right, and the predicted labels. So this is the format that you have to put the inputs in. So the true in this case are iris underscore y underscore test, right, and the predicted ones are, the ones predicted using the svm module. So we'll say svm underscore norm dot predict, right, and this one will take just one argument, which is iris underscore x underscore test underscore norm, right? And I think I need another parenthesis to close the print statement. So right, so now you can see here different things. So you see that, the precision and recall and the F1 score for class 0 is very, very good. And the support essentially tells you how many data points that you have for this particular class. But now you can see that, for class 1, although the precision is 1, but you have a recall which is lesser than 1, and the overall F1 score, that's why gets impacted because of that. So, and you can kind of make sense of all of this based on the confusion matrix. So that's the basis of all of this. Again, we had 4 as the support for this, and similarly for class 2, and the overall accuracy is 90% based on 10 data points, and then there are some more specialized averages that takes into place. And these are some things that, comes up over and over again. Sometimes you see them in the Kaggle competitions as well, that, you are being judged based on the F1 score. The F1 score is a very good representation of the classification errors. So, all right. I think in the same line of doing stuff, so I'll just quickly introduce decision trees, and then if we have time, we'll go into deep learning today and continue it tomorrow. But let me actually quickly show you one more example. So that's a decision tree. It's also a classifier. It's based on, it's one of the formats of the random forest. Like these have the same class, same type of philosophy behind them. So we'll use the decision trees from scikit-learn. So from sklearn, we will dot tree. We will import the decision tree classifier. We'll import decision tree classifier. So that's our decision tree classifier that we'll use, and we'll call it dt underscore class. That's our decision tree classifier. We will say decision tree classifier. And again, there are a bunch of parameters for this. So one of them is minimum samples leaf, and you should look at this. So this is basically how the segmentation will be done when a decision has to be taken, right? So it's again similar to a lot of the parameters in the random forest as well. So okay, so I'm going to change this to 6, and I'll make the depth of the tree. So depth means how many levels of the segregation you want. So the more the depth, the more prone you are to overfitting the training data, but more level of details you capture. So there is always a, what do you say, a balance between how much of depth you should have and what should be the optimum depth. And for that, you try to use cross validations and things like that. But in this case, we'll use a maximum depth of 5. Okay. And once we have this, we will try to use it to fit our data, right? Again, in this case, I'm going to use still the normalized data, right? So the normalized data is essentially a better data to use for this decision trees as well. All right, so that should give me the decision tree, right? So I did the fit with the normalized features and the output labels. And then what I'll do is, for one more time, I'll plot the confusion matrix and see what happens in the prediction. I'll put the dt underscore class. I'll use the input feature set iris underscore x underscore test underscore norm. And the output labels, the true output labels are iris underscore y underscore test. And the color map that I'm going to use is again going to be the blues color map. Okay, again, the same result. So none of these classifiers could actually do a perfect classification on the test data set, right? But I wanted to show you that, decision trees are also something that you can visualize very nicely. So you can actually use different visualization techniques to visualize the tree that you have kind of designed or have got as part of this, specification of the classifier. So to do that, we'll have to define the name of our features, right? So what are the different input features? Because the tree would look nicer if you have the names instead of having some random column 1, column 2, and things like that. So I'm going to put the names of the features as a list. And I know that the first column is sepal length, second column is sepal width, third is petal length, fourth is petal width, right? So it's going to be um, the features, right? And again, there is a part of the code which I'm not going to talk about in details, but this is, a thing from the sklearn.tree that you can import plot tree, and I'm going to paste it in the chat window as well, just so that you guys can also have it if you are following along. So you can see that, if you execute this, it actually tells you. So we had defined 4 levels, 1, 2, 3, 4, right? And then this is how, the decisions were made. So if the sepal width is less than equal to this, then it goes into the second one, and then it would classify it based on the different, these values. So it's a great way of, visualizing and making sure that the classifier, you can give some interpretation to the classifier is what people like to tell about these kinds of methods. Could you paste the features line for sure? Yeah. All right. Whew, that was a lot of models that we covered, and I know we didn't cover in details on the theory, but this is more on an application based class, so I hope you guys already came with some background of things. If you haven't heard about these things, it might be a good place to go and look at Wikipedia or Google and search each of these classifiers. But all these classifiers are very, very standard. And one good thing about sklearn is that you've seen that all of these things have the same formatting, right? So it's just that you have to import the right module, but they have the exactly the same formatting of specifying the classifier and doing the fitting and whatnot. So you can actually have a function that takes in all the different classifiers that are there that you think are useful for your problem and automate the whole process. And then you can specify a list with hyperparameters that you can run overnight with a lot of compute, and then do the hyperparameter tuning to come up with the best possible classifier. And this is done very, very often in hardcore data analytics as well. So Yeah, just wanted to bring that before you guys. All right, so this is where we are done with the scikit-learn. So we'll go forward with a brief introduction of deep learning, and then we will, continue tomorrow and see where we, pick up stuffs for the deep learning modules. So all that you have seen here are not what is termed as deep learning. All of these are called, the normal machine learning workflows. But deep learning is something that has come up very, very rapidly, specifically because of the compute power that we have, right? So we have a lot of compute nowadays. You can already see that, you have a pretty heavy machine virtually that you could get from Google using Google Colab. So a lot of computation advances has actually enabled us to use the simple neural networks, feed forward back propagation neural networks, and make them much more parameter driven, and that is how deep learning has come into place. So we there are different packages that you can use for doing deep learning. What I'll try and touch base upon in tomorrow's class is this package called Keras, right? So Keras is a wrapper around around backend, machine learning modules such as TensorFlow or Theano or whatnot. So these are different packages. You might have heard about them. So TensorFlow is a very famous one that came from Google. There is another famous one which people use a lot, which is called PyTorch. It has the backing of Facebook. And then on top of that, there is this package called Keras. And Keras is something that gives you a little bit easier way of implementing some of the machine learning models. Okay, so and we can look at what Keras actually the website of Keras, which is how we start any package in the beginning, right? So this is Keras. It's a simple, flexible, and powerful way of doing deep learning for humans, and you can see that they have a lot of examples, and they are being used by a lot of different organizations. It's pretty powerful. So it's actually a bit of a trouble to get a machine learning module to install in your computer, and if you have a GPU in your computer, to make sure that it uses your GPU and whatnot. But in Google Colab, you have TensorFlow and Keras already um, pre-installed. So we'll just use that for our workflow, and we'll use what is called the MNIST data set. So in this case, the problem will be a famous machine learning problem, which uses handwritten uh, digits, right? They have been scanned, and there are like grayscale pictures of those in a database that has come from Jan LeCun and his lab, and these are famous people, in machine learning. But the MNIST data set is constructed from NIST, which is National Institute of Standards and Techniques, I think. So that's essentially the database that came from them, and there various people have applied various things on them, including came nearest neighbors that we had used before, some of the SVMs and neural networks, and we're going to use convolutional neural networks, and we show a very simple convolutional neural network that you can use for the MNIST data set. So to do that, we will do one special thing in our notebook. So by default, in our notebooks, we do not have a GPU assigned to us, but the data set that we're going to use is a little bit heavy, and it might take a little bit of time to train the models and execute the whole thing. So we're going to open a new notebook, and in here what we will do is we'll go into runtime, and we will change the runtime type, and we will select the hardware accelerator as a GPU. So GPUs are graphics processing units, and TPUs are something that has come very, very recently. These are tensor processing units. So TensorFlow and Keras also uses TensorFlow as its backend. Um, so a lot of machine learning is done using tensors. So there's a specific processing unit for tensors. It's actually very fast, but we're not going to use that. We're just going to use the GPU, right? So we're going to select a GPU and we'll save this so that once we connect our machine, we also not just get a machine, but we also get a GPU out of it, and we're going to use the GPU for our training purposes. All right, so let's actually look at the data set at least, and then we can continue from there tomorrow and start introducing Keras and how we define a CNN model, convolutional neural network model. So the MNIST data set. Okay, so this is a data set that's out there. You can download it in different ways, but the Keras module has like a scikit-learn module had the Iris data set. The Keras has the MNIST data set in it. Okay, so we can load it using the Keras module. So we'll load MNIST data set using Keras Keras library. Okay, so what we'll do is we'll say from Keras dot datasets, we'll import MNIST. Okay, so and our first step was, remember, to visualize the data and to make sure that the data that we have imported is good enough. So to do that, we will use again the matplotlib's pyplot. So I'll say from matplotlib import pyplot, right? So I'll use the pyplot, and again, remember these things should be repetitions for you guys. We are trying to plot this in the Colab notebook itself, so we'll use the matplotlib keyword as inline. All right, so once we have this actually loads or rather imports the MNIST function, and from there you can actually load the data set. So now we'll load the data set from this imported module, load the MNIST data set. So what we'll say is we'll say train X, comma, train Y. X are the input features, which are basically 2D images with pixels in black and gray, and you'll see that right now. So that's our train. And then they have a test data set as well in here. So test X, test Y. So you didn't have to split them explicitly. You can do that as well. But the way the MNIST load data set works is essentially you can separate the train and the test based on what is there in the Keras module. So we'll use this MNIST dot load data with all the default arguments, right? So that should load the data. It'll take a little bit of time. It's downloading it from this particular data set that's in there in this particular format. So .npz formats are how you save the NumPy arrays. It's one of the nice ways to save the NumPy arrays. Okay, so while this is downloading it, let's actually go ahead and try to write some more pieces of code and see what we can do with the data once we have it downloaded. So let's say we want to see the size of the training and test data. It should be done by now, right? Yeah, I think it's done. So let's see. So we'll use a print statement. We'll say train X equal to, so this is a different style of specifying a print statement. So we had previously done using commas, but a percentage s would give you, percentage gives you the control of over a variable that you would define later, and s is basically the particular thing that you want to output using that. So you could have easily used the comma, but I'm going to just show you a different kind of a formatting in here. %s, and then this was actually very, very popular back in the days. So this is, Python 2.5, 2.6 had this kind of a formatting. What I'll do is I'll say train x.shape. Remember that was how we get the shape of NumPy arrays. So, and then we'll have train y.shape. Okay, so this will give you the training data size, and I'll do the same with the test data size as well. So I'll say test, and this one as test x, and this one as test y. So we want to see what is the size of the data set. So now it has given me an error, and that's because I have specified the test capital Y. So I could either change this, but I think it'll take some time to download. So let me just keep it as this and change this into test capital Y. So this is your input data set. So you have 60,000 images with 28 cross 28 as the dimensions of the 2D images, and you have 10,000 images as your test data. So it's pretty huge data set, right? So okay, so last part, I'm quite aware of the time. We might go a couple of minutes over today, but let's just plot a few images and see what the data looks like. I think that'll be a good point to stop as well. So plot a few images from the loaded data. Okay, so I'll use a for loop, right? For I in range of, let's say, I want to plot 9 of these. I want to plot it in a subplot. Again, all these should be repetitions for you guys. I'll define the subplot. I'll say pyplot dot subplot. And the way this will happen is 3, 3, 0. So that's the first one. And I'll do it some bit cleverly by putting it inside a for loop. And I'll let you guys find out if you have any problems with this syntax. Let me know tomorrow. But essentially this will help you plot inside the for loops, and it'll go from one subplot to another based on this for loop that we have defined. And what we'll do is we'll plot the images using the ImShow. So remember, we had used this in the last week's lecture to plot 2D plots, and we'll pull in stuff from the train X. So we're going to plot stuff from the train X data set, and the color map that we will use is from the pyplot library. We'll get the color map, get underscore CMap, and we will use the gray because this is a grayscale image. Okay. And that's it. So we'll just, after all of this, we will say pyplot.show. Hopefully this works. Some error here. Pyplot. Yep. So all right. So these are your input images. So this is what we are going to classify. So you can see that these are handwritten images, not machine images. So this is 504192131. And you can plot a lot of other randomly as well, other images from the test data and whatnot. So essentially all of these have their corresponding labels in the Y, and we're going to use a machine learning model, a CNN based model, to actually train the machine to take input these images and classify them with the correct numbers. Okay, I think that's a good point for us to stop. What do you think, Michael?
Wow, Vishal, this is great. This is really a great course. Thanks a lot for walking us through this. A lot of information, but I think you explained it in such a very good way for us to follow. And for the class, I know it's a lot of material we covered. You walked through almost all the models that is out there, from nearest neighbor, logistic regression, random forest, neural network models, support vector machine, decision tree. So that's a lot. So thanks a lot. And for all of you, we're going to send the video right away. I know a lot of people want to go through this, multiple times to get the concept Yeah, I'll be sending out the video right away and the class notes for us to practice. But thanks a lot, Vishal. This is great. I look forward to tomorrow. I've learned a lot myself, so I'm looking forward to tomorrow when we go more into the KNN in Keras. Thank
Yep.
you, everybody.
We'll do the CNNs tomorrow. Yeah, we covered the KNN today,
Oh,
but
yeah,
we'll do
sorry, the
the
CNN. Yeah,
convolutional neural networks. Yeah,
perfect.
which
Yeah.
is
So this is great. Thanks a lot. I think, I know we went over time just a few minutes, but this is really great stuff. So feel
Oh,
free to use the Slack channel if you have questions as you go through the videos and the material. Let's continue to interact, on the channel so that we can learn from each other. For tomorrow, we're going to start with a guest. We're having two guest speakers come and give us a lot of overview on Python, the jobs that are out there, on resume tips, just a lot of helpful information that I think will be beneficial to most people in the group. So we'll do that for the first 30 minutes. Then we'll continue with CNN, not KNN, tomorrow. But
yeah, a
thanks a
lot of
lot.
NNs out there,
I
but
know.
hopefully this wasn't too overwhelming for you guys. I know it was a little bit fast, but tomorrow, I mean, I think I covered most of the things that I wanted to. So tomorrow we'll keep it a little bit relaxed so that, if you guys have some more questions, we can definitely take that forward before loading you guys with or overloading you guys with more information.
Yeah, that's good. Thanks a lot. I think it was fun. There's a lot to learn. We'll send this video, spend some time, go over it. Lots of material, but you can apply a lot of this once you get the concept here. You can actually apply to other data sets, which will be sending out in your project, and you can get your hands on one of these data sets and try to, follow some of the lecture material, and you should be able to walk through it. You know. Thanks a lot. I know everybody's waiting for the video, so I would not waste too much time. I'll let you guys go. We'll send this out, spend some time later today to go over it so that by tomorrow you're kind of very refreshed. And you can bring your questions once you've watched the video and you have looked at the lecture notes. Thank you, everybody.
Thanks, everyone. Bye.
Michelle, great work.
Thanks. Bye.
Thank you.
Thank you.
Thank you very much.